Hello folks, after a long time I'm back with this lecture of magnetic field. So today my topic is effect of magnetic field on a rectangular coil carrying current. Till now we have studied up to the effect of uniform magnetic field on a current carrying conductor, straight conductor. And what we saw was, because of that, the interaction of a magnetic field of the conductor and the external magnetic field causes a force, and that force is called as lowering force, whose direction could be found by the left hand rule of Fleming. Now what we do is, we now take a long conductor in the form of wire, and we change that into a coil. So I have a sample of the coil, somewhat like this. So this is a wire that has been turned into a coil. So I bent it several times. Let us say current comes from here. So let me say current comes from here. It goes there like this, like this, like this, and like this. So now I place the coil somewhat like this. I place the coil somewhat like this, somewhat like this, and then I apply magnetic field. So here North Pole and here South Pole. So I apply the magnetic field. Then what happens in this current carrying coil? So that is our question of today, and will be our dealing will whole be focused on this. So if I place a rectangular coil like this, and if I allow current like this, current coming like this, like this, and like this, and if I apply magnetic field like this, what will happen here? So for that, let me draw a diagram, and I'll have two types of diagrams. One is a 3D diagram. 3D. I'll be watching this thing. Somewhat like this. It is like this, and I'm watching with this angle. So I can see this in front. I can see this in the back. In the other case, I'll be just be seeing like this, direct view. So in such a way that I can see this, but I don't see anything backward. So let me draw the diagram first. So I frequently require a lot of time to draw the diagram. So let me see whether I can draw it fast or not. So this is the pole of the magnet. So one pole of the magnet. I write here N like this. Then I have another pole of the magnet. So this will be S pole. Like this. So it will be dotted because it is at the other side. It will be dotted. It's because it is at the other side. It will be at the other side like this. So I am writing S in reverse, because when you look from this side, it should appear like this. Now I draw the coil somewhat in this way. So the coil is slightly slanted like this, and then wire like this. Now what I must do here is, this portion is towards us. So that's why it will appear a bit thicker and longer as well. So let me make it bold like this. So this thing is appearing thicker. Now it will gradually grow thin to that side. So let me make it thin, gradually thin. So it is thinner here, a bit thicker, like this. So here also it has to become thicker this side and thinner that side. So it looks okay, I suppose. So let's name them. So it is P, it is Q, it is R, and I'll not name it as S, I'll name it as U. And current is coming from this side, and the magnetic field will be from N to S. So I haven't drawn it here, I'll draw it later in the other side. So the next figure will be like this. So this is somewhat this type of slanted view, and here it is direct view. In the direct view, I will be seeing only QR. I can see only QR. I won't see anything else. So it is north. So this should be south. And the QR should be somewhat like this. So the center, this should be the center, and QR should be somewhat like this. This should be QR, so uniform thickness. I cannot see this P and U because I'm watching in that manner. It is direct 2D view, so I cannot see anything of the back region. So this is Q and this is R. Now current is going in this direction here, current going in this direction. Now the field lines will be somewhat like this, field lines. So from N to S, I have got field lines like this. So I will draw one field line directly through the center. So one field line through the lower edge like this. So let me draw a triangle here, triangle. So Y I will tell later. So this is O. Now in QR the current flows like this. So in this Q current is coming from P. So that's why I will use here dot circle. It's because current is coming towards us. From P to Q means from that side to this side, current coming towards us. And in R we have current is going from R to U. So current is going in this manner. So current is cross here. So this is current and this is also current. So this is the 2D diagram. So now let's say that this angle and this angle is equal to alpha. So this is an angle formed by this plane, angle formed by the plane of the coil with the field lines. So the field lines are going like this, the plane of the coil is like this, so is that angle. So it is this angle. So this angle is angle alpha. So let me write here, this is a 2D view, often called as direct view, and this is a 3D view, often called as perspective view. So this is the complete diagram. Now let us allow current and see what happens in each member of this coil. Let us first consider PQ. So PQ is a conductor. It's a part of the coil, but it's a straight conductor in which current is coming from P to Q. So current coming from this, magnetic field is like this. So now let's apply the left hand rule. So in the left hand rule, this finger represents the magnetic field. So this is the magnetic field, and the current is represented by the middle finger plus others. So as I have often repeated, somewhat might do like this, some might do like this. So I prefer to do like this. Then the force will be upward. So that means this region PQ will experience force in upward direction. So that means the force here will be in upward direction. So here it will be in upward direction like this. This is the force, this is the force. Similarly, in R we have a current is going from R to U. Current is going here. So if I apply the same rule here, the force will be like this. So magnetic field here, magnetic field, and this thing has to go that side because current is going to that side, and this is the force. This is the force. So that's why the force should be in downward direction like this. So this is the force. Now we have an item here in which this side faces force in this direction and this side this direction. So it must give rise to a couple or a torque. They should constitute a couple and give rise to a torque. Now let us see what about this QR and PU. So they also are members of this coil. Though it is not dealt with in text, we should know the nature of the force here. So QR is like this, current is flowing somewhat like this, and magnetic field is here, magnetic field here, current here. So that's why if I extend my fingers like this, so in Fleming's left hand rule, it has never been said that the angle should always be 90. Angle could be anything. It's because it is guided by the formula here. This force is equal to BIL sine theta. So this theta is the angle between the conductor and the magnetic field. So that's why here what we have here is so this is the conductor QR and this is the magnetic field. The angle between them is this alpha. So in that case my fingers will be like this. Magnetic field here horizontal. This QR is slightly slanted here, and this is the direction of the force. And the force depends on theta. If theta is large, the force will be high. If theta is less, the force will be less. But it has not been said that if theta is not 90 degrees, there will be no force. No, the force is there. So here it might be less force, and if we do like this, the force might be higher. The force is there. So that means this QR will experience a force in this direction towards the observer. So the force will be towards the observer like this. Similarly, in this PU, the direction of current will be like this, reverse. So in this PU region, the force will be in that direction. In PU, force is in that direction. In QR, force in that direction. It applies along the whole length. So this force on QR and PU, they exactly cancel each other. They might try to slightly lengthen the coil, but they exactly cancel each other. So they have no effect on the stability of the system. So what is affecting is the forces on this PQ upward and this RU which is downward. And these two forces give rise to a torque. So that's why now I have to find the torque. So the torque is equal to F, one of the forces in the couple, force into perpendicular direction, perpendicular distance between the lines of action of the force. This is the line of action of force F. This is the line of action of force, another force F. So this is the distance between them. So that's why F into QO. So QO is the separation between the lines of action of the forces F and F. So tau equal to F into QO. So I think there should have been clarity on why there is a torque. Now this QO is equal to, in this triangle I have got cos of alpha is equal to QO divided QR, which means this QO should be equal to QR cos of alpha. So I must have, this is F into QR cos of alpha. Also let's go for what is F. So F is equal to BIL sin theta. So the force experienced by this PQ, so we have to go for that length, BIL. And sin theta is the angle formed by PQ with the field lines. So PQ with the field lines. Now PQ is situated somewhat like this. It is like this. So let's see here. These are the field lines, and PQ is like this, So what is the angle? The angle is this. The angle is this. So this angle is 90. So it might be difficult to look from there, but from my side I can say, if I look like this, this angle is 90. If I look from here also, this angle is 90. So PQ is like this, field lines is like this, so that's why this and this should be 90 degrees. So I will have this F is equal to BI, L means let's say simply say PQ, L means simply say PQ, BI into PQ, then sine 90 degrees into this QR and cos alpha. Sine 90 equal to 1. So I must have BI is there. I will group this PQ into QR together and then cos of alpha. So now PQ is the length of the coil and QR is the breadth of the coil. So if I have this coil once again with me, PQ is this PQ and QR is this. So this length into breadth gives us the area. So this is the area of the coil, which is equal to, or tau equal to BI A cos alpha. So for one turn of the coil, it is tau equal to BIA cos alpha. But if we have got n turns, and we do, because we never use one turn only, because one turn only gives a certain torque or force. If we multiply the turns, the torque or force will be higher. So that's why we often use n turns. So for n turns, this will be equal to, tau will be equal to BINA cos of alpha. So I use this terminology because this appears to be name of a lady name, which is used in almost every part of the world. In every ethnic group, they have got some name as Bina. So that's why I often tend to use this. Now, since there is cos alpha, it depends on the angle. So when alpha equal to 0, alpha 0 means that this angle is 0. At that time, the position of the wire is like this. This is the magnet, and yes, at the time the coil is like this. So this is PQR should be exactly like this, and these should be the field lines. So this is QR, alpha 0. So at that time the field line should be like this. So it means that alpha is equal to 0. So that's why in such case we will have tau is equal to b I n a cos of 0, which is equal to 1. So equal to simply b I n a, and it is the maximum value possible. Now if I do the same for alpha equal to 90, so if I want to make alpha equal to 90, so when alpha equal to 90 degrees, the diagram will be like this. So this is the N pole, this is the S pole, and the QR will be like this. This is QR. This is how QR will be situated. So this is Q, this is R. Now if they are the field lines, let me place this coil here. So if the field lines are like this, so this is alpha equal to 90 degrees. So in such case I will have torque is equal to, so therefore tau is equal to b I n a cos of 90 degrees equal to 0. So in this case there will be force, but the torque will be 0. Here they have got force, so this is the force F, this is the force F, torque is there. Here we have got force F and a force F, but the torque is not there, because force alone does not guarantee torque. It has to have certain separation between the line of action. Here we have, so here the forces are there but the torque is absent, and here the forces are there and torque also is maximum. So this is the expression, and this is the special cases that we can deal with. Now if you place a coil like this, it has got everything it has got. If you place like this, no torque. The only position where there is no torque. But in all other positions, every other positions, we have got torque. So that's somewhat different cases here. So it may experience a force. It doesn't mean that compulsorily there is a force. It might experience a force. So force is experienced when the angle is not 90 degrees. So this is the expression for the torque.